I will be starting shortly. Please stand by. Welcome to Microcontrollers with kingernorth. This is episode 14, using ultrasonic sensors with CircuitPython and Arduino. That's going to be today's topic, so let us go in and have a closer look at what we're doing. So here we are. So just to start with, there's the boards that we're going to be looking at today. Today we have an Arduino Uno and we are connecting it to a sensor. This is an ultrasonic sensor. This is the Adafruit Feather M4 Express. It is also connected to an ultrasonic sensor. In fact, these are exactly the same type of sensors, along with a couple of LEDs that I have here that I'll be talking about when we get to that part of the programming. Some extra features you might want to add into your control program, but they're not required to make the ultrasonic sensor work. Good morning, Walter. Welcome aboard. So these are the basic parts we're going to look at, and these are the basic little sensors. And I just wanted to talk about these for a moment because this particular one, up in the top left corner of it, way up in here, it says this is a US-100, which is not the most common version of this sensor. And yet when I put it down here beside the other ones, they all look basically the same, and they are basically the same. These are all ultrasonic sensors. This one here has got some special properties I'll talk about in a moment. But there are many versions of these out there, and you have to watch which one you get in order to get the right one for the application. And the beauty of these ultrasonic sensors is not only can they detect items that are in front of them, but they can actually give you a real measurement coming back to tell you how far away that object is. So there are good uses for this when you want to tell when you're getting close to something. These are very common. You'll see these on robots, roving robots. Sometimes they're even mounted to servos so that they turn, and they're constantly watching for objects that are in their path. So they do avoidance detection. What they're doing is they're looking for an obstruction, something like a wall, a chair, a person, and then they can steer around that. The decisions can be made inside the program on what to do from that point on. So that's what basically these ultrasonic sensors are for. In model railroading, we can also use them to tell how far they are, and I'll talk about this when I get to the CircuitPython example, is we might want to detect when something's going down a blind tunnel. We have a lot of times what we refer to as off-track staging or hidden staging, and this means that it's not easily seen by the operator. So there's going to be times when you're going to run into a stub-end yard. In other words, it's going to be a dead end, and you're moving your train down a tunnel, but you can't see the end of it. You can actually create indicator lights or actually put up a display to tell you how far from the end of it you are, and you can even act on it and even turn power off to rails and things like that if you really wanted to. So we'll talk about those. But first of all, let's talk about some of the different sensors that are available. And for that, I've actually got a little view here that I can look at when we get into our main program. So let's hop into our main program and let's have a look at these different types of sensors that are available. They look very similar, all of them, but what happens is we have four basic types that I've listed here. There are more than this, but there are four basic ones. The most common one out there I've listed at the top. That's the HC-SR04. It works, it's cheap. You actually go onto eBay, you can get these usually on eBay for about $1 a piece or somewhere thereabouts. Give or take a little bit. If you go on to places like AliExpress or one of the other direct suppliers from China, you can actually get them even cheaper than that. I've seen them down as low as about 45 cents each. and that's in Canadian funds. So they're pretty cheap if you want to get them. But there's a problem. They're limited. They're not as universal as we would like. They're one of the original boards of this type, but they only work on 5 volts, and they require 5 volts. So that's going to cancel out some of your microcontrollers that are out there. Now, the Arduino Uno is a 5 volt board, so it's not a problem. But many of the others that are out there, especially the more modern boards that have other features that the Uno does not have, or they've expanded on that dramatically, a lot of them run on 3.3 volts. So they need the 3 volt connection. And there's also a possibility of using communications. So it's just not capable of doing that. It's the most basic, simplest version of an ultrasonic sensor. The next type is the type we're going to be using today on these boards, and that's the RWCL-1601. Now that one, I bought these a couple of years ago. I picked these up for maybe a 10 or 20% premium over the price of the cheapest version. But the advantage with these is they work on both 5 volts and 3 volts equally well. They have logic step downs on them so that they will work on both 3 volt and 5 volt without any issues, and they just work fine without it. And it's nice, simple hookup, but they're universal, so it doesn't matter which microcontroller I'm connecting them to, they're going to be fine. The replacement seems to be this next one, which is the RCW0006. That seems to be the replacement for the one I'm using here today. I had trouble relocating those ones that I used. It just looks like this is just a more modern, a newer version of the one that I have here today. The RCW0006 has the same specs as the 1601. So you can use it on both 5 volt and 3 volt. And the last one is this other one that I have here. This is that US 100. And that one is kind of unique in the fact that it actually has UART communications, which is a serial type communications. So it allows you to hook that up and talk to it, and you actually can get more information than just distance out of it. You can actually get temperature. Believe it or not, it actually has a temperature sensor on it as well. So both of those things are available, and you can utilize that. The problem with this board, and this is what I don't like about this board, is it requires 5 volts to the board itself to operate. But the logic pins, which are the communication pins, they're referred to normally as trigger and echo, but those 2 pins will work on 3 volts or 5 volts. So those are universal, but you still need 5 volts to feed it, which eliminates this regular usage with most of your other microcontrollers, the more modern versions. Even some of the Arduino, you can get nanos that are 3 volt, and you can get micros that are 3 volts and different ones like that. So it's nice that it has the serial communication, that you can actually get more positive connection to it. What I don't like is the voltage issues that they have with it. So for myself, I prefer one of the middle 2. And those are the reasons why I like those. Now, to connect this up, I'm going to show you how to do that. I'm going to have to shrink this image down a little bit, and I'll go over here. The basic connection for these, unless you're using the UART control, this is identical for the other boards. And in fact, the UART board, the US100, also allows you to run in just standard mode as well. It actually has a jumper on the back, so you can run it like this as well. And when you run it like this, basically what you have, whether it's an Arduino or one of the others, and this picture just happens to be for the HC SR04, but they're the same for the other boards as well. So what you have here is you supply it with power on the red line, and that can either be 5 volts or 3 volts depending on which sensor you've used. You have a ground connection that connects to the ground pin, and then you have 2 other pins called echo and trigger. They are connected to 2 of the digital I/O pins that are on the board. There are some helper files where they'll connect them to the analog ports, 0 and 1. You could do that as well. Typically, though, they work really well if you just use them on digital I/O pins. And you have no reason to go, oh, we're garbled again. Jeez. All right, let's just do the old stop and restart. No reason to go, oh, we're garbled again. I don't know what it is. That was last week it did that, and this week it's doing it again. So give me 1 second here with the broadcast. Okay, so let's see if that's now working.
Okay, so let's see if that's now working.
All right, seems to be fine now. I'm actually seeing it. I listened to it for a moment. Don't know why it's doing that. It did this last week too, for some strange reason. Hopefully, it maintains good quality now. Thank you, Walter, for that help. I don't know why it's doing that. It did it last week. It dropped a few frames, and now we have 0 drop frames. Okay, I'm gonna have to actually set up my stuff a little bit different. Now I can see the number of drop frames without having to look separately. So it looks like we're fine for the moment again. I'm going to have to watch that for next week. I'm going to make myself a note. All right, so the voltage here is basically, like I was saying before we reset, power goes to power. Common black is the ground, which is just connects to your ground or common pin on your microcontroller. And the last 2 pins, the echo and the trigger, just connect to digital I/O pins. There are versions of helper files that will ask you to connect it to A0 and A1. But I find that for the most part, just hooking it up to 2 of the general input-output pins works just fine. And we're going to show that when I create the program here in a moment. So I think we're going to be fine with this. So let's get rid of that and let's open up our Arduino program itself. So here's the start of my window. And what we're going to do is I'm going to move this one out of the way. I'm going to move my extra US 100 out of the way that we're not going to use. And we're going to concentrate on this so I can zoom in a little bit. There we go. And I can show you what's connected here. So this is very simple. On here, there are 4 connections. The US 100 has 5 connections on it if you're using it. So it has a 5th wire on it. But basically on the front of it, if you get into here, they have an echo and a trigger button, and this one has 2 grounds on it. The other ones only have a single ground. So we have the ground wire is black, the red wire here is power, and then we have the yellow and the white wires connected to those 2 different ports. So let's build our program. Let's go ahead and build our Arduino program. So we'll get started here. First thing I want to do is I just want to go up to the top. Let's put a title in here, and we're going to save this file. So we're just going to call this Ultrasonic _01, and I'm just doing that to make sure it's different. And I'm going to put my name in here, and we're going to create this file, and it actually won't take very long to find it, to build it. It's actually pretty short. Let's see here. I can spell would be a help. So let's go File, and we're going to go Save As. And I'm going to pick my location, and I'm going to do it this time. I'm going to go in here, and I'm going to connect to my documents. Where are my documents? There they are. Electronic Show. And if I come down here to the ultrasonic sonar, we can actually see I actually have one here already built. But I'm just going to create a new one here, and I'm going to give it the name, and I'm going to give it the same as what I said there. It's just US for ultrasonic _01, so it's unique. And I'm just going to go save. And now we have a file that we're building with. So this is anything, this is our normal. So I'm going to skip by some of the comments, but I'm going to put some in just so we don't forget where things are. So the next thing we would do is we would include any of our helper files. So let's do that. Include any required helper files. And the nice thing is here, when we're doing it this way with this ultrasonic sensor, we don't need any. We can actually get away without adding any extra files whatsoever. We're just going to run this with just the straight Arduino, which makes it as simple can be. So the next thing we're going to have to do is define any variables and pins. Well, we know we're going to have a couple of pins to use, so let's go ahead and do that. We're going to need an echo pin, and we're going to need a trigger pin. We're going to need those things. So, and these are just giving us an actual address. So let's do that as integer. And we're going to call it echo pin, and we're going to make that equal to, in this case, 2 is the way I've got it wired up. And we're also going to create another pin for our trigger pin. So trig pin, and that's going to equal pin 3. Those are just what I happen to chose. They can be almost anything. They're not a problem. And this is based on original code that can actually be found on the Arduino site itself, on arduino.cc. They actually have some helper files in here too, some helper sketches. And this is where I based this out of, and then I modified it a bit. We're going to actually leave some room here because we're going to have to throw in a couple of variables, but we're going to see what those are going to be. So let's go to our void setup. So in here in our void setup, we have to assign those pins. So very simply, we just use pin mode, just like we've always done with Arduino. So we're going to go to pin mode, and let's set up the 2 pins. So I got trig pin. It doesn't matter which one I do first. These are both going to be the same, basically the same. But this is an output. So our trigger pin is going to be the output. And that's the way we're going to be using it in this program. The next one is pin mode is going to be the echo pin. The echo pin is what's receiving the signal. This is ultrasonic, which means it's sound waves. So what's happened here is that we are actually going to transmit a sound out that's in the ultrasonic range that we don't hear, and we're going to receive it back on the echo pin. So we're going to transmit it out. It's going to transmit out through one of these two units. They look the same, but one's actually a transmitter and the other one's a receiver. And that's what happens is here. You take a signal out of here. So if I move that over there, I take it out of here, I take it out, I bounce off an object, and I come back. And what I'm going to do in my program is I'm actually going to read how long it takes for that signal to be from the time I transmit it to the time I receive it. And it's a very, very short amount of time. So that's what we're going to do in this program, is we're actually going to measure that amount of time. And based on that, it's going to tell us how far an object is away. So that's what we're going to do in this thing. Now, the other thing I'm going to do is I'm going to include one more part in my setup, and this is going to be my serial monitor because we want to get feedback to say where this thing is. I want to be able to see it, and seeing it on the serial monitor, actually it's just serial begin. We might as well do this properly. Serial begin, and we're going to start that at a fairly low frequency. We don't need to be fast, so we'll start it at 9600, which will be fast enough, and we'll see what's going on here. So this is what's going to happen. So basically what we're going to do right now, we've got a little program here. All I've done is assign 2 pin addresses. I've set up my trigger pin, which is the transmit, is going to send out a sound wave. So it's an output, and the echo pin is going to receive it, so it's the input. And what we're going to do is measure how long it takes from the time we transmit it to the time we actually receive it. So we're going to do that in the loop. So let's jump down into the loop of our program now. And this actually is a relatively short program to do what we want here. So we'll get rid of this first of all at the top. We're going to have our own comment. So the first thing we need to do is we need to give ourselves a starting point. So we're going to actually go to digital write, and what we're going to do is we're going to force the condition of this trigger pin. So in other words, of the transmitter. So I'm going to go in here, trig pin. And what I'm going to do is I'm going to tell it to go low. By telling it to go low, basically what I'm doing is I'm turning off the transmitter to give it a starting point, just so it has no signal coming in right now. And that's what we want. And then we're going to create a slight delay here. Now, to give you an idea, what we're going to find out is we're going to look at this, and we're actually going to put in a small amount of delay in here. But the regular delay we've been using is in milliseconds, and that's way too slow for what we're doing today. These sound waves travel very, very quickly. So we're actually using a new version of it that we haven't used before in this series, and it's actually going to be microseconds. So we're talking, and I obviously spelt it wrong. There we go, microseconds. And we're going to keep this down to 10 microseconds. So we're talking, this is a magnification huge over what we've got in milliseconds. And I think if in order, if I'm correct, it goes milli, nano, micro. So this is like 1,000 thousandths. This is a much, much faster timing sequence. This actually allows us to do things very, very quickly on the clock. So that's what we're going to do there, is we're going to do that. So we're going to turn it on. So what we're going to do is we're going to start off by, actually I can keep this really short. I just need a couple of microseconds. Because what we're going to do is we're going to go to our next step. So I'm going to leave a space just so we can see where these steps. So this is step 1. Turn off the transmitter. Once we turn off the transmitter, then we're going to turn the transmitter on. So what we're going to do is I'm going to copy this line here because we're going to be dealing with the trigger pin. I'm going to copy it, I'm going to paste it, and instead of going low, we're now going to turn it on, so we're going to go high. Now what we need to do is we need to set how long do we want to turn this on for. And this is where I'm going to use this again. And again, I'm going to use copy and paste just because it makes my life easier. And this is where I'm going to go, and I'm going to do it for a measured time of 10 microseconds. So now once I've done this for 10 microseconds, then what I'm going to do is I'm going to go back up here, and I'm going to turn this off again. So I'm going to come down to here, and I'm going to paste that. So what I've done is I've created a 10 microsecond pulse of this ultrasonic. So that's what I've done in this location. Then what we need to do is we need to figure out how long does it take for it to get back to us. So what we're going to do is we're going to be creating here something called duration. So we're going to have to create a variable for that, but we'll do that in a moment. So duration is going to equal to something, and this is a nice little feature because this is a predefined code within Arduino, and it's called pulse in. And I'm going to read that on the echo pin. So I'm going to go to the echo pin, and I want to read that, and I want to know when it goes high. So even though it's a input, what I'm looking at is I'm actually reading for it, and I want to get I want to know when this is true. And what will happen in here is this thing will start counting amount of time. And then what happens is it'll say, hey, when the echo pin receives the signal, this is true, allow this statement to continue. So this is actually going to give it and record the amount of time it takes. So it's actually pretty neat that you can actually measure that with this. So this is something that's already built in, which is really, really handy for us. So that's our third step that we've done. So first step is we turned off the transmitter. Then we pulse the transmitter for 10 microseconds. Then we read and we actually say, how long did it take to get there? So then what we have to do is we have to turn that into a calculation, a distance. So we're going to create a variable called distance, and that's just going to be equal to our duration. And there's a fixed number for this. And this fixed number is actually going to be 0.32. Now, 34, sorry. Got to get the right constant in here. There is a constant for the frequency that's being sent out. So what I'm going to do is I'm going to multiply that by 0.34, but then I'm going to divide it by 2. Now, you might wonder what's going on here. So what's happening is here, there's a certain amount of time that it takes to travel out here. When I measure that in microseconds, I have to multiply that by 0.34, but because it has to send it out and then return it, I have to divide it by 2 because I only want to know the length of 1/2 of this cycle. So I need to actually divide by 2. So that's something just we have to do to make it work. So that's what we're going to do. And then the last thing we're going to do here, and by doing it multiplying it by 0.34, I'm actually measuring that distance in millimeters. If you want to measure this in centimeters, you would go 0.034. You would decrease the amount of duration that you're multiplying by. to give you centimeters. So it can be either displayed as millimeters or centimeters with this constant. So let's display it now. So all I'm going to do is I'm going to go to serial print, and I'm going to create myself a nice little description here. So this is distance, and we're going to do that, and we're going to put that in quotes, bracket, semicolon, and then we're going to do the next part, which is we're going to actually put the value in there. Serial dot print, and this is where we're actually going to go in there and actually put that value distance in, just like that. And finally, we're going to end this with our measurement value. So it's going to be serial dot print, and this will be the end of our line. So we put the ln in there for the line return. And in here, I'm going to put in quotes. I'm going to leave a space and then mm for millimeters. Close that off. And then one last thing we put in here, just so that it's not screaming by reading it constantly, we're actually going to put in we're going to put a little half-second delay in here, just so it gives it time and we can actually see the numbers rather than see the numbers stream by. Now, I did mention something here. We have two variables that we created. We need to add those to the top of our program so that we have them defined properly. And there's a couple of things that they need to be. So let's go in here. And the first one we're going to define is the duration. Now, because it can actually measure for quite a distance, and I never mentioned how much distance these things measure for, these ultrasonic sensors. They'll actually give you a measurement down to about 2 centimeters is the way they typically do it, so 20 millimeters, and as much as 450 centimeters. So they'll actually give you quite a bit of distance involved in there. And that's actually quite a few feet if you measure it in feet and inches. It goes from very close to a fair distance away. So 450 millimeters. There are slightly different versions on different sonics. I've seen them up as high as 600 centimeters. And basically 100 centimeters is a meter, which is a little over 3 feet. So these things can go quite the distance. The problem is that these do not go out in a straight beam and out. They actually go out in a bit of a cone shape. So what happens is you can start picking up objects to the side the further away from the sensor you go. And I'll talk about that when we use it in a train application, how that works for us. So what we're going to do is let's add these. So the first one, the duration, the thing is we can end up with a very large number in here depending if something's extremely far away. So what we need is a long number as opposed to the regular integer. We're going to create a long number, which is going to give us a great big 32-bit number, so it can get into quite a long amount of time. Because don't forget, we are dealing with microseconds. So we want to we don't want to make sure we don't run over our other values. So this is going to be duration. The other one is in millimeters. Well, even in millimeters, even if we're doing it in millimeters, 600 centimeters, which is the long version, is only 6,000 millimeters. So it easily fits within an integer. So let's just create this as an integer, and we're going to create this as distance. You could create this as a long as well, but it just takes up more memory and nothing else. So let's go over what we've got here in the program before we validate this, and then we'll upload it into this board and we'll check it out. So all I've done here is I've included I gave myself a title. I included any helper files that were required, and there are none. I defined any variables and pins. Well, I need 2 pins, pins 2 and 3. I've actually got duration and distance, so those are the 2 variables I need. In the setup, I set up both the output and the input pins. The output being the transmit, which is the trigger pin, the echo pin being the receive, which is the input pin. So I've done those. I tell it to begin the serial monitor so that I can get feedback, so I can see how much distance has gone by. Then in my main loop, I've actually created a digital write trigger pin low, and I've delayed that for 2 microseconds. So that's the first step. So that's turning off the transmitter. Then I turn on the transmitter for a period of 10 microseconds. So it's a measured time frame of 10 microseconds. Then I look at the duration, and I actually wait for it to bounce back in, and I read it. And this is something that's already built into the program. So it's already in the Arduino language. And pulse in, we're going to read it and see how long that 10 microsecond lasted and how long it took before we got it. So we're expecting to see that 10 microsecond burst come back in. Then we look at our distance. We do a calculation based on hard numbers. So it's the duration times 0.34, which is nothing more than a constant. This constant is 4 millimeters. Divide by 2. The next part is we're just going to print out the results, and then we're going to delay by a half a second before we repeat it. So let's see if it's happy first. So let's verify this, see if I missed anything and put in any commas or missed a bracket when I programmed. I think I'm okay, but we're going to check. And it does. It says I'm fine. And down here at the bottom, it says done compiling, so I'm happy. Then I'm going to make sure I can find my Arduino board, and it is right there. My Arduino Uno is on COM4. So I'm going to go ahead and I'm going to upload this sketch. So it's uploading it right now. It says it's right there. It finished compiling. It's uploading, and it's done. So let me turn on the monitor. And I will bring that into the screen so that we can see it. And there it is right now. It says that something's 158 millimeters away, which is not very far, but it's actually bouncing off of my monitor next to me. So this is where I'm actually going to run into space issues. If I put my hand in here to the image, I'll show you. It's now reading down to 45, 46 millimeters. As I move my hand closer to the sensor, that distance is dropping. I can get down to about there. Once I get down to about 2 millimeters away, then you can see my numbers. Look at how they bounce all over the place. What happens is there's not enough physical distance with the angle for the signal to come out and bounce back. So you actually have to be at least 20 millimeters away, sometimes a little bit better than that. So it actually likes being at least that far away. That's about as close as you can get. And as I move away, we can see that number's increasing, and it's actually fairly accurate. If you were to take out a measuring tape and measure that, you would find that that would be very, very accurate. In fact, let's move this back over there so you can see where it is. I'll put my hand just inside the screen. So at this point here, I'm 130 millimeters away roughly. As I move forward slowly, we'll see that number drops. Continues to drop until I get down to about that 20 mark, just over 20. And then I've pretty much minimized what I can do with this thing, so I can't get really any closer. If I do, I just don't have enough time for the signal to travel out and back. So I can get reasonably close to it. So that actually works very well. And I can actually see my hand come back out. And when I bring my hand out, I'm going to come back up to that 120 mark roughly right there. And that's about as close as to 120 as I'm going to be able to go. There's slight variations there because let's face it, my hands aren't flat. They do move slightly, and it's just reading as best as it can. But it's pretty accurate. So this works. So that's really all there is to this program here. So that was that program, and that was basically there. So now I haven't got all of the comments in here. If I wanted to throw comments in, I would definitely comment on what each of these steps are. I do have a completed version of it, and you can always send me a message, and I can send you a completed version with the comments in it. And I've got all that set up in there, and it's the same program, just it has all the comments built into it. So really, that's how that works. So hopefully there's no questions on that. That was pretty simple. That's actually very simple to use. So what we're going to now do is we're going to move on to the CircuitPython version of this, because in the CircuitPython version I've added a little something that would make it better for model railroaders. So let me just move this one out of the way. I can take that one out, and this one's here somewhere. There it is. Basically it's the same thing. In fact, actually I'm going to turn it this way just because I can get to more distance. And you can see lights are flickering here, and I'll explain what those are when I pull up the program. But we're going to go into this one because this one's done slightly different. Now, this ultrasonic sensor is the exact same model as the one I used on the Arduino board. So there's absolutely no difference in there at all. It's the exact same board, but this one works on 3 volts or 5 volts. So this way I don't have to search which ones I'm using at the time. So let me turn off my Arduino code, and I'll turn on my CircuitPython code. So this is what it looks like in CircuitPython. In fact, actually, I'm going to bring that up. I'm just going to increase that just a little bit to make it a bit easier. And I'll walk you through what the code is here in CircuitPython. So at the top here, this is a fully documented version. So this is basically the same principle as what we just did. It's just done in CircuitPython. I will admit this might have been a bit easier in Arduino this time, but this one actually does have a helper file for it. So we start here at the top of the program. So up here at the top, we have 3 lines. The first 3 lines are telling me nothing but the information that I've done in there. That's my title. And I've noted in here that I'm using an RWCL1601, but it's in reference to an HCSR04 because they are basically the same sensor, except this one allows you to use 3 volts as well as 5 volts, either or. And this is created using my Adafruit M4 Express and which version of CircuitPython I'm currently using on here. It says include any required helper files. Well, unlike our Arduino, we have to include everything in CircuitPython. We've talked about this before. So I'm including time so that I have delays. I'm including the board so I can address the pins. Digital I/O, I'm importing digital in, out, and direction because I need to set up an output pin. An output pin and an input pin. And this is going to be strange, but this is the way it's done here. Then I'm going to set up my object for the sonar. Oh, I'm sorry. I'm going to import Adafruit HCSR04. Now, HCSR04 is basically, that is the base board, but because this works identically to that one, it's the same helper file. That's why I included it in my comments. So I have that reference in there. So I have included this file into my libraries folder on my CircuitPython. The next thing I'm going to do is I'm going to set up the object. Now the object is slightly longer than the page, so let me just zoom out just a little bit. It's going to be harder to read, but it says sonar equals Adafruit HCSR04.HCSR04, and then I set up my trigger pin and my echo pin, and they're set up to pins 5 and 6. So that's really what I'm doing there is I'm setting up those 2 pins. They're going to be tied to 5 and 6. And because of that, actually I don't have to do anything else. This next part is LEDs. This is not required for the sonar, for the ultrasonic to work in the first place. The ultrasonic sensor, which is basically just a sonar unit. This is set up, I've added 2 LEDs to this board connected to pins 11 and 12. I've connected a red LED and a yellow LED. So now let's see how this works for us. So in my main program, this is actually really short. What I'm going to say is my distance equals sonar.distance. Well, because this has a helper file, all those steps that I created inside of the area in the Arduino where I had to walk through the steps where I had to turn off the trigger, turn on the trigger for a given amount of time, turn off the trigger, turn on the echo sensing. When I read it, see how long it took to sense, and then from there I could do my calculations. This does it in one line. Distance equals sonar.distance. It just did it all. So it's actually very simple in there. And then what I've done is I'm doing something here called try instead of just print. I could just print the distance. What happens in here is for some reason we lose it and we don't get this number. We can't get that value to come in. It has an except. So as long as it works, try will be true, and in this case it'll print the distance, and we'll see how that works. The except will happen if there's a runtime error. It'll keep retrying it, and then it's going to delay for 100 milliseconds. So that's our delay that we normally have at the end of our whole thing. Now what I've done here is I've added in another statement here for these LEDs. So let's first of all just turn on the serial monitor. When I do, I can see I'm getting a decimal point. This actually gives me decimal points in this one. So right now it's reading about 150 millimeters. I put my hand out here. It's down to 40, 30. Actually, my numbers are off. I can tell you that right now. Let me bend that back a bit. So what's happening with my distances today? Oh, I know why. Because this is not measuring in millimeters. This is measuring in centimeters. So probably where I print distance down here, I should probably put in I could put in another print statement if I wanted to. But what I should be doing is I should be measuring the distance and then telling me myself it's in centimeters. That's why my numbers look small. Out here, I'm actually, if I tilt this board, I can tilt this up towards an open space. And let's see if I can get lucky and find the opening in the room. There we go. We're at, the doorway was at 280 centimeters away, which is like 3 meters away. If I bring it down here, it's actually picking up a table that's behind me that's about 1.5 meters away. So that's 150 centimeters. So now I'm using centimeters instead of millimeters. So what I'm doing here is I'm bringing my hand closer. And just to give you the same type of thing here, you can see the shadows getting there. I can get down to about 2. I start going below that and it gets really weird on me. So that 20 millimeter gap or that 2 centimeter gap is the same, and doesn't matter whose board you're connected it to, that's what that sensor is capable of reading to in the minimum area. So what I'm doing is I'm reading out a much further distance out here. My hand's quite a ways away. In fact, I'll actually move that up to there. And then you'll see that as I bring my hand closer, you can see the shadow coming in. There's my hand getting closer. I'm down to 5, 4 centimeters, 3.2. I'm down into 2 centimeters away, and right about there is about where I'm going to stop being able to read. Anything closer than that, my numbers start going back up because it just can't read it. So that's the reality of it. So that actually works. In fact, I can actually sit this just inside the image, and you can see without my hands there, it will read that distance. And it's pretty consistent. It fluctuates a little bit here and there, but it basically says it's 3.196 centimeters away. In other words, it's about 32 millimeters away right now. So it's actually giving me a pretty accurate reading, and nobody's touching it. It's just going out and seeing that. Now, what I wanted to show you is what we can use in a model railroad. I'm going to take this little sensor away. I'm going to bring this out to about here so that we can get some distance on it. I can now see that I'm better than 20 away. This isn't going to work out. I'm going to have to go this way. Just to show you, I want to show you what happens with the LEDs. So what happens in the train layout? This is where I think this is good for a blind or a hidden staging when you're going to a stub track, when you're trying to find the end of the track. Anybody who's operated model trains, which I know Walter has and some of the other people that watch this, is when you run your train back in there, you might be dropping off a set of cars inside a tunnel. And very often what they do on a train layout is you bring loads in one place and you take empties out, or you do the reverse when you're doing it. So you'll have a load of coal cars. They'll come in full, and basically you put them into a stub track. Then what happens is somebody removes the loads if they want to make it look nice, or in theory what's happened is they get unloaded, and now you're going to pull out the empties. The problem is you can't see where the end of that track is. So what I've done is I've actually created myself a couple of LEDs here. So let me scroll back up in that part of the code. And I'm going to show you I created a yellow and a red LED. So just LED red, LED yellow. And this is the code that I've used to define this. So what I start with is an if statement. And I say if the distance is less than 30, in other words 30 centimeters, 300 millimeters, then I'm going to do what's inside here. If it doesn't, turn off both. I just say else, and I say make the value of the yellow and the red LEDs false. In other words, turn them off. So right now in that image right here, they are both off. The yellow and the red are both off. But my distance is also greater than 30. It's at 45 right now. So we can see that. As we move forward, what I'm going to do is I'm going to bring this in here, and I am now at, let's see, I might need a little bigger object. Oh, I don't want to go that close. I want to stay out here. I'm going to go out here about 25. 25, 26. So at 25, 26, what happens in the program is my yellow, it says, is it less than 30? Yes. So it says yellow LED, in other words, LED yellow value, make it true. In other words, turn it on. Turn on. So this is the same as having a digital write and setting it to high when you're in Arduino. So this is LED yellow value equals true. So it's on, and my yellow light is on the board. It may be hard to see there. In fact, if I put that down there, if I give you a shadow, you can't see it. I'll get my arm in there. So we can actually see that that yellow light is on. If I move away, it will shut off. So I'm going to put that there. So it sees the front of the locomotive traveling in that direction. And then what I've done is I've said, hey, if it's closer than 10, so as the end of my train approaches, I can see now I'm 11 centimeters away, 10, and there, it went under the 10 value. If the distance is also under 10, so if it's under 30, then I can check to see if it's under 10. If it's under 10, turn on my red light. If it's greater than 10 but under 30, turn off the red light. So as I pull out, my red light will turn off. As I push in, I can see now I'm getting near the stop block of my station, and I can stop my throttle. And I've given myself a fair bit of room. I can still move another 8-9 centimeters without any issue, without wrecking my train at the end of the block. So this is where this comes in to be an advantage. So this allows me to actually measure the actual distance from the end without having to put in multiple infrared sensors or things like that as I'm approaching a yard. But this does have a downfall. This works great with a single track that's coming to a stub end. If you're going through a pull-through staging yard, this is not good because the sensor would be in the way of your train pulling out now. So that doesn't work. That's where the infrared just says, I'm positioned here, I'm positioned here. This one actually warns me as I'm getting towards the end of a tunnel on a single sensor. And I can have multiple lights. In fact, actually I could go here and I could put a green light in for when it's not yellow. I could actually have a third light that turns on that says green, saying, yeah, the tunnel looks empty at this point. So I can do any number of things with this. I can switch this around all over the place. So this gives me a warning telling me I'm getting close to the end. I'd slow down my train. And as I would jump in here and get real close, oh, there's my red, stop my train, drop off my cars. And that saves me from derailing my train inside at the end of the tunnel, which, believe me, has happened more than once, and it's always fun when the homeowner or yourself is trying to dig out those cars from the end and they're no longer on the tracks. So that's just something to be aware of. So we can actually use this for distance. If you're building robots, where this comes in really handy is I can see it right now. My distance is greater than, it's greater than 30 centimeters away right now. My robot can travel at regular speed forward. As my wall gets closer, oh, I get a warning. I could use that to tell my robot to slow down and start to turn. And if it doesn't turn fast enough, what can happen is here I get closer than 10, I tell my robot to stop so that I don't run into the wall. Okay, so I can actually use this to measure my distances away. Think of a Roomba. A Roomba finds its way around one of the Roombas that are out there, those little robotic vacuums that are out there. What they do is they have sensors similar to this on the inside, a little more advanced version of this, but the same basic principle. And what they do is they measure their distance away from the wall. And when they get near a wall, they say, okay, I'm approaching a wall, and they might slow down, and they are finely tuned. They actually finely tune theirs. This wouldn't be right on the edge of the unit. This would be set back behind usually a black piece of translucent glass. You don't even notice it. And what it says there, hey, I know that exactly 5 centimeters away from the sensor is the edge of the robot. That's where my sweeping arm reaches. So when I get to 5 centimeters, stop traveling in that direction so I don't slam against the wall. And then it can travel and it continues on down. And there'll be a number of these sensors around in a circle around the vacuum. So as it approaches, it knows it has to stay away a certain distance, long enough for its little sweeper that comes out to pick up the dirt along the edge of the wall, but without slamming into the wall. So you don't actually have to make contact with it. So these are really handy for robots. These are so cheap that you can use these on toy robots and you don't have to worry about them. And for applications for trains, they work great for stub end tracks. If you need to take a measurement so that you can have warning lights at the end of the track so you don't run into the train into the wall at the far end or the bumper. And I thought I'd mention this here. The reason I wouldn't use this if I had multiple trains coming in, here I am on my side track. I'm going to try and create as if I'm coming down the side. My hand is not actually lined up in front of the sensor. It's about a track width away. The problem is I'm picking it up because of the angle. I can move out a fair distance. Let's see how far I can show you this. If we zoom out and I move this right to the back edge, I got to keep my LEDs on there. My LED is on right now up at the top. Now it might be hard to see, but even if we come down to the red LED, I'm just going to bring my hand down like a fist until I get there. There's my 10. Now watch when I go to the side. It starts to fall off, but look how far over I've moved my hand before it fell off. And I go the other way, and again, I'm over quite a ways from center from this thing. So if you're looking at the yellow light only, I'm way over there before it shuts off. So these do spread out rather quickly, these lights. So they're good for a single approach inside. And if you're worried about this being a tunnel and reflecting off the walls, you actually don't get much reflection off of the side of objects. You do get a little bit, but what you can do is you can line this with something like foam, something that would absorb sound waves. So if you put a little bit of foam on the sides, you wouldn't see any of that signal, and you can get yourself a nice narrow spot to go down. So that's why it works with a single track, not with multiple tracks. And that's basically what there is to ultrasonic sensors. So let's just zoom in here a little bit more. In fact, we can zoom in. Let's try once more. So that's your whole setup right there. Nothing fancy. We have a microcontroller board. We have power, the red wire here. We have black wire for the ground. We have the white and the yellow are the two triggers, the trigger and the echo coming back to the board. And in this case here, I've added two orange wires for my warning lights and just wired them up with a resistor back to ground. This is all working off of 3 volts on this board. This exact same wiring, just change the resistor values to something slightly higher. You can run this off of 5 volts. So you can do the exact same connections with the Arduino. Doesn't matter who's you're using. Both work really, really well. And they're actually fairly simple to work with. I don't know if you have any quick questions. I'll give you a moment if you want to type in a question in there. I know, Walter, you're still watching. I think I've covered it. Very simple to program regardless of which microcontrollers you're using. Very handy. They're cheap. I would suggest that you grab yourself 2 or 3 of those at least, maybe a couple more, and play around with them and see what you do. And the fact that they connect to various pins, you can set up various triggers and everything. There's no reason why you can't use more than one on the same board. Especially in Arduino, they're really easy because you're actually creating this whole helper file within the program, and you could create that as a subroutine and then just have each one access it when you want to check a measurement from that sensor. All right, so I think that concludes it for today. Thank you very much for watching. Hopefully the audio didn't go too bad too quickly. I'm gonna have to keep a better eye on the dropped frames in the future. I don't know why it's doing that on the first start, but it did that last week and we did it again this week. Restarted it during the show and it seemed to be fine. I'll keep a close eye out for this next week. And other than that, I think we're good to go. For anybody from the states that are watching this, from the United States, happy 4th of July today. To our Canadian friends, myself included, happy belated Canada Day. We had that earlier this week. So those 2 birthdays are up. And everybody else, just stay safe. Play around with your electronics. Enjoy it. Give it a try. And looks like we're going to have some fun with these. And this is the whole idea with this stuff, is don't forget, we're here to have fun. If we have fun, we might even learn something along the way. So until next time, I should be back next week. I've got another project I'm working on. I don't know if it'll be ready for next week, but there'll be a topic next week. We'll see what that is. Don't forget, you can always follow me and subscribe on my YouTube channel right here, kingernorth. You can also watch for my tweets. Follow me on Twitter at kingernorth. That way you get the information. I send out tweets the day before the show, and also about a half an hour to an hour before the show, just to remind you. And that takes care of it for then, till then. So enjoy, have fun. Come on back next week for episode 15, and we'll see what the topic is. Thank you very much. Have yourself a great day.